Okay, welcome everyone to the second installation of the Langtangen seminar on scientific computing. Today we're very happy to have Paola Antonietti from Politecnico di Milano, who is going to talk about modeling neurodegenerative diseases. Just a brief bio about Paola before we start. So Paola is an Italian mathematician who works in Milan, but is also the head of the Laboratory for Modeling and Scientific Computing, known as MOX, as you may know it. Paola received her PhD in 2007 from Pavia. He's very interested in numerical methods for PDEs and scientific machine learning, biomedical computing, and so on. And she's won many awards, including an ERC Synergy grant, and has published over 100 papers. So we're very happy to have Paola today and to provide her some ideas on her research and some perspective in scientific computing. So Paola.
Oh, thank you. Thank you very much, Thomas. Thank you, Maria, and thanks to Simula Institute for this invitation. I'm really honored and glad to be here. So what I would like to discuss, it's not an easy topic because in Simula there are worldwide experts on modeling the brain, so I'll try to do my best. So it's a research project that we started, I would say, 3 to 4 years ago. So after many years that I work on computational geophysics and more from both theoretical and applied stuff, I decided that it was a time to change somehow perspectives. And I used the power of mathematics, which is a universal law, to try to move more towards application in the field of life sciences, and in particular, try to use mathematical models and scientific computing power to better understand the mechanism that sustains and drive neurodegeneration. So first of all, let me thank the people who have been crazy enough to join this journey. So Francesca Bonizzoni, Ivan Fumagalli, Stefano Pagani, Nicola Parolini, and Nitin Kumar are faculty members here at the Department of Mathematics and at the MOX Laboratory. Mattia Corti just received his PhD a couple of months ago, working with me. And Caterina Lemersaglio, she's a PhD student. She just came back a couple of days ago after a very exciting research stay in Simula with Maria and with Kent. So thanks for hosting her. She will come back next year, so she's very excited and she's looking very much forward. So what is the starting point? So discussing, this is we have collaborations ongoing with the Neurological Institute, Carlo Besta here in Milano, is literally across the street from Politecnico di Milano. And after discussing with them, so the idea that they transmitted, they are expert on so they are responsible of dementia track for patients that exhibit some form of dementia, and then most of them they are diagnosed with the neurodegenerative disorder. Is that so? There's a common path. This is known like a prion hypothesis. So some of neurodegenerative diseases, including Alzheimer and Parkinson's, that are the two diseases that have the higher incidence, are a result of a gradual neuron degeneration, which leads over time to decline, so cognitive decline and a dysfunction of the motor system. And it is known, well, there's enough consensus that there's a central mechanism that sustains such a process, such a biological process that involves proteins misfolding. So at a certain point of the person life, for reasons that are not fully understood, there's this mechanism in which proteins start to misfold and they aggregate and they diffuse through certain paths, which are more or less known, and forms toxic aggregates. So this is known as a prion-like paradigm. So the idea is that even though different pathologies are characterized by different proteins that undergo to this misfolding, aggregation, and diffusion process, the general mechanism is the same, and it's known like prion-like paradigm. For example, to make an example, so in Parkinson disease, it is known that the protein that sustains this process, so that undergoes misfolding, is α-synuclein. For Alzheimer's disease, there are two proteins that at different time scales started this this misfolding process, and these are known to be the beta amyloid and the tau protein. So despite the different characteristics of the involved protein, the idea was to try to construct a mathematical model able to model this phenomenon, and then to specialize it according to the different pathology, and then to make it personalized for each patient. And what are the main challenges, and why mathematical modeling and scientific computing can be somehow of support in the clinical practice of neurologists? So I think that this is a picture that gives an idea of the time scales. It's a qualitative picture, but it renders the point. So if you look at the at the orange line, so in the x-axis, you see the different clinical stages. So from a cognitive normal person, MCI stays for mild cognitive impairment. It means that the first symptoms appear, but overall the quality of the patient is still good. And the last part is fully conclamated dementia. And this is qualitative, the evolution of the clinical function. From so in the y-axis, you see the switches of certain biomarkers that can be measured, typically through the spinal fluid. So symptoms appear during the first stages of mild cognitive dementia, and then the clinical function deteriorates. To make a comparison, please look at the red line. This is the evolution of the abnormal concentration of amyloid-beta over the years. And as you see, so the concentration of misfolded beta amyloid starts to increase much more before any symptom appears. And basically, as long as the first mild cognitive impairment appears, the level of saturation is already a plateau. And this is an irreversible process. The question is, which is the time scale over here? So this is a process that can take decades. It means that a patient that now approaches a neurologist because it has some forms of a mild cognitive impairment has started the process of neurodegeneration even 30 years ago. So that's an overview of why mathematical modeling, to better understand the pathways and all the intricate mechanism that sustains this process, can be of help to better understand. And it is also known in the scientific community, in the neurologists, scientific neurosurgeons, scientific community, that there are, so the prion-like hypothesis is strongly interconnected with many other physical processes that sustain and drive neurodegeneration. First of all, there are the so-called waste clearance mechanism. I mean, at Simula, there are really worldwide experts in constructing and then solving numerically models for better understand how fluids behaves, so how fluids flows in our brain. The idea is that since nature is perfect, everybody of us has a a backup mechanism. And so every day, an healthy patient completely wash out 3 times the cerebrospinal fluid that is formed within the brain. And these serve as a waste clearance mechanism to drive waste substances produced by brain functioning, including the aggregation, the aggregates of misfolded proteins. And it's well known that this system deteriorates with aging. It's perfectly normal, but to some extent, it is also known that people that have some form of neurodegenerative diseases in these patients, the waste clearance mechanisms are even more impaired. So these, to some extent, sustain the aggregate, the deposit of the misfolded aggregates. That's one of the other mechanism, and also due to neuronal loss, late stage patients undergoes a loss of mass. This is due to neuronal loss. So these are postmortem images of a patient, an healthy patient of the left, and a patient diagnosed with Alzheimer's disease. And you see the ventricles are much enlarged, and this clearly completely change the balance of fluids, so how the fluid flows and all the clearance mechanism. So there are many intricate physical phenomena that that are strongly interconnected and plays their role in the evolution of neurodegenerative diseases. And from the mathematical and modeling viewpoint, this induces a number of challenges or opportunities to better understand or to better describe these all this phenomenon. So suppose that I want to stay at the organ scale. So here the spatial dimension which I'm interested in is the organ scale. So I will look at the picture from a macroscopic viewpoint. Let's focus on time. So as already discussed, prion distribution and accumulation and neurodegeneration and remodeling due to brain atrophy is a very long time scale process. So it takes ages or decades. At the same time, the brain state and waste clearance mechanism are known to happen at the scale of hours. But that's not the only multi-scale. We have an even shorter time scale, which is related to heartbeat pulsation, so how oxygen is supplied to our brain, and an even shorter time scale, which takes into account the fact, well, we should take into account the fact that one of the symptoms of patients, for example, with Parkinson, but not only, are epileptic seizures. It is known that at a certain point it might happen an imbalance propagation of the electric signal. And this is an even shorter time scale. So the idea, ideally, is to construct a model which is able to see the link and to merge the link between these different interplays. We are not there yet. So let me try. So what I would like to discuss today is so some of these problems taken independently, with the idea then to put them together in a long journey. So let me start with the prion distribution. So modeling how misfolded proteins diffuse in the parenchyma, and then if I have time, I will discuss so models for waste clearance and then for epileptic seizures. And that's somehow the plan. I'm not sure I can touch all the points, but I'll do my best. So what can we safe from the modeling viewpoint to describe the phenomenon of misfolding and then diffusion through axonal pathways. There are many models in the literature. So let me skip this part. I'll try to argument looking at the equations directly. So the simplest model that can be used to describe this process is the so-called Fischer-Kolmogorov model. So it has been proposed for biological population evolution or gene competitions. The idea is that you have a population. In our case, the misfolded proteins. You work in the relative concentration. Here, the unknown is typically C, which in our context is the relative protein's concentration. So you look, for example, at the unit cube of parenchyma, and you would like to know in this elementary volume how many, so the relative concentration of misfolded proteins over the total number of proteins. And you can write down your model. So in the general case, here you have a source term. In our application, this is 0 typically, and you would like to study how this relative concentration evolved over time. This is the diffusion process, and this is the conversion process. And this constant here, alpha, is very important, because first it has to be calibrated. That's a complicated story. But it tells you the ability, like in an infectious disease, the ability of an alt protein to of a misfolded proteins to get in contact with an alt protein and convert it into a misfolded one. So like in an infectious disease, modeling. And then you supplement, as usual, with the suitable initial and boundary conditions. And in our application, so the diffusion takes place, so the diffusion tensor is typically an isotropic part, which has to be weighted by a coefficient, plus an isotropic part which takes place along the axonal directions. And these terms is in general, so in the application under consideration, much more large than this one. That's the simplest model. So you work only with one field. This can be formally derived from a more complicated model. So historically, this was typically, this is the starting point where you are not happy to work only with misfolded proteins concentrations, but you really want to work with the two fields. So healthy proteins and misfolded proteins. This is called heterodimer model. Here you have basically two sets of equations in the two different fields that are coupled. And you can also take into account more physics-informed detail of how this conversion takes place. But of course, the price you have to pay to be more physically informed is that you have more parameters that at the end you have to calibrate. That's not the end of the story, because these are homogenized models. You can even go more complicated from the mathematical structure viewpoint. And now you work with a full set of agglomerates, and you also have the stage, so the microscopical stage between, so that underlying the process of misfolding. So this is called the Smoluchowski model. Here you have n different fields, and you are also able to incorporate in your model microscopic information to some extent. So we have worked and we have developed on the three of them, so different level of mathematical complexity that of course then implies a higher complexity from the point of view of the numerical discretization, the analysis and the validation and verification step. But to give the main idea, let me stick on the simplest, and I'll then show some results with the heterodimer model. So the starting point is that so the typical domain where we want to solve our nonlinear partial differential equation is very complicated. So in order to properly describe all the sulci and the different heterogeneities between the white matter and the gray matter and the white matter, you need a very fine grid. This is from the geometrical viewpoint. From the mathematical and numerical viewpoint, the typical solution of Fisher-Kolmogorov equation is a traveling wave solution, which means that you have a quite smooth solution that exhibits a sharp front, which moves over time. And you want your numerical scheme to capture all these features, because otherwise you miss the important information. So you want to capture very well this steep front, and you want to capture very well at the numerical level the wave speed propagation. So combining these two requirements, the idea was, okay, I start from a very, very fine grid. This is a two-dimensional section, but this is completely dimension independent in such a way that I'm able to correctly describe all the geometrical features. So all the sulci, all the layers between the different materials. But that's too expensive. Think in 3D, this means immediately the exascale computing. So the idea is that I agglomerate elements. And this is going to be my computational grid. How I do agglomerate from here to here, so I won't enter into the details, but now we do this with graph neural networks because they are very robust, they are fully automatic, and they can preserve the distinction between different materials automatically. Now, this is my computational grid. I have fewer elements. I'm free to rise the polynomial order of my approximation as much as I want to gain accuracy, but I need a method that can support these crazy-like elements with a lot of small edges, because the edges remains of the same size of the original mesh. So the idea is that you can go for a fully discontinuous approximation that's perfectly robust to handle this kind of elements. They are prone, this is the original DG methods, they are prone to high order approximation in an element by element fashion. So you can rise the polynomial degree only in the cells where you are interested. And they are prone to massively parallel implementation, especially on graphic processor units. So that's the overall idea. Let me try to be slightly more quantitative. That's a toy problem, so it's nothing connected with neurodegeneration. The idea is, suppose that I want a fixed accuracy. Here, I think I put it in 10 to the power minus 8. And this is my original grid, 42,000 triangles. This is the agglomerated 534 polygons. And suppose that I want to compute the error. This is here, I'm cheating. I know the exact solution, but just to make the idea that you can make the error much, much smaller. So saving computational power. Here you see the square root of the number of degrees of freedom by the right interplay between agglomeration and rising the polynomial degree. And we have the same kind of results, but instead of measuring the square root of the number of degrees of freedom, we have the CPU time. So it's a different way of conveying the same message. Now, going back to our original equations, I want my mesh to be made of agglomerated elements. so I have no limits on the convexity of the elements, on the number of faces each element can have, nor on the relative measure of each face compared to the diameter the face belongs to. So there are some mild irregularity conditions, at least for the theoretical setting. We never vary. But there's a piece of theory that if you really want to go, for example, to fully anisotropic elements, for right now, we don't have the theoretical setting. This is my semi-discrete approximation. So I want to look for any time t of my relative concentration that satisfy this equation. So I come from the Pavia PD school. So first space and then time. I know this is not the only approach, but for the purposes of this talk, I will follow the path space discretization and then time discretization. And these are the three ingredients. So this is the term that corresponds to the diffusion in a fully DG setting. So I have the volume term, this is classical, and then I have to stabilize controlling the jump across my polygons and my polyhedral to make sure that in the limit, I glue the jump, because my solution is going to be discontinuous from one mesh element to the other. And this ensures consistency of the formulation, and this restores symmetry. So that's plain DG. The volume terms remains exactly as they are because these are volume. Please notice that in the DG setting, these are block diagonal, or you can even make them fully diagonal matrices. I have the linear part and then the nonlinear reaction term. What you can prove for the semi-discrete formulation is that, the semi-discrete formulation is well posed for any time t. You can carry out a rigorous theoretical analysis, optimal bounds with respect to the mesh size, slightly optimal with respect to p by a factor 1/2, but this is known in the digit setting. It's a technical issue on interpolation. What you can't prove, and we are working on this, is that in this plane formulation, CH, the scheme is structure preserving, which means that you cannot prove that the continuous solution, the true solution, you can prove under a certain condition on the nonlinearity and the initial condition that the solution is a relative concentration, so remains bounded between 0 and 1, or 0 and some threshold. That's not the case, so there's no free lunch. So this is not the case for this formulation, but we have proposed alternative formulations to make sure that we can ensure positivity preserving of the semi-discrete solution. Oh, sorry. No, I spoiled. Sorry. I spoiled the video. Let's go back. Okay. What else you can prove? So I'll skip the theoretical results. We have also carried out a full verification and validation, which I want to discuss later, as well as sensitivity analysis. So how these conversion factors enters into the evolution. And that's a validation test case carried out for a patient diagnosed with Parkinson. So the image were reconstructed from medical images, and in this case, we use a conversion factors taken from the literature. So that's a qualitative validation test case. What we can say at least is that the evolution in terms of the regions of the brains that are subsequently affected by misfolded α-synuclein are consistent with what is observed in the clinical practice. And please notice that for α-synuclein, there's no way to through digital imaging the deposit of alpha-synucleins. So all the knowledge about progression of the disease is inferred by neurologists based on employing other measuring techniques. So it's never a direct measure. This is based on symptoms or on other kind of tests, but there's no way to measure the deposits of alpha-synucleins, at least nowadays. That's another validation test case. So this is a male patient in a very late stage disease of Alzheimer. For this patient, we had both a structural MRI as well as diffusion-weighted MRI, which we employed to reconstruct the axonal directions that enters into the definition of the diffusion tensor. And for this patient, we have two scans that measure the deposits of beta amyloid, because for beta amyloid, you can, through a PET scan, measure the deposits of misfolded proteins. So we used as initial datum the first scan, and then we carry out our simulation, in this case, in a very, very shorter time frame, because so this is not a simulation, this is data from the PET scan. And this is sections after, so these are simulation, and this is what happens after 2 years. And they were consistent with, unfortunately, the medical data. Please notice that what I'm plotting here is not really the concentration. This is the scheme we have improved to ensure positivity preserving. So this is a slightly improved variant of the scheme I presented before. Now, what about if I want to use a more informative model? So let's move from Fisher-Kolmogorov to a more complicated model. There's no free lunch, so the mathematical analysis is instructions, and the verification was consistent with the theoretical findings. The point is how the two different models behaves, one compared with the other. So do they provide the same level of information? So this is the same test case for which I discussed before, and I compare the two schemes. And what I measure is the so-called activation time. So here the colors refer to a certain region, which is, so the first time for which the relative concentration of proteins exceed 95%. So you can assume at that point that that region of the brain is completely sick. First of all, what you can infer from these images is the evolution of the pathology through the years. And this is consistent with what is observed in practice. And if you compare the two models, Fisher-Kolmogorov seems slightly faster in terms of activation time. So it seems that going for a more informative model, more expensive also, some provide a slightly better approximation, at least of the activation times, or at least for the test case we have carried out. This is the result in 3D for the heterodimer model. What we can conclude is that, as expected, as it is known in the field, a stable pathological equilibrium is reached. The evolution pattern fits what is known, so from the lower brainstem to the mesocortex and then to the neocortex. This is what is known in the clinical practice. And the last step is try to, that's a very rough first tentative to try to validate the model more from a quantitative viewpoint. So what we have tried to do, so we have focused on the substantia nigra, and we have tried to measure how our numerical results compare with clinical data, where here clinical data are so-called biomarker abnormality curved. So these are so our blue line is reconstructed in this way for the heterodimer model, and this is can be assumed to be a good approximation of how the biomarker behaves, and this is the comparison with the clinical data. Of course, there's not a precise match, but at least the trend seems to be more or less matched, particular in, so the stages 3 and 4 and 5 and 6, and this is the classification stage. This is the symptomatic phase. So it's where the symptoms appears and the number refers to the severity of symptoms. Now, I think I have still like 10 minutes. Okay. So maybe I'll go very quickly through so the other topic I would like to discuss, which is how this is connected, well, ideally how we would like to connect all this research with the brain waste mechanism. The idea is that we would like to construct a model which is able to describe how the fluid flows in the brain. You know much better than me about this, so I'll go very, very quickly. And the idea is that we would like, again, to exploit polytopic grids, and ideally to have block models that can be merged according to the kind of details we want to inform our models in a pretty straightforward fashion. So here the example is on a very simple and idealized geometry is, on the one hand, I would like to have a multi-compartment poroelasticity model in its dynamic formulation to model so the tissue. And for example, this is a really not precise Stokes equations in the brain cavities. So this is the ventricles. You have to use a little bit of imagination. And this is the little space we have between the brain and our skull, which is full of fluid. What you can do, well, you can go again for a PolyDG approximation. So you have boundary condition, interface conditions, which I want to incorporate in a weak sense, so I can glue the model, very natural. And what you end up is basically that you have your multi-compartment poroelasticity equation for the poromechanics part. Then you have the fluid for the other part, and the interface conditions enters naturally in the formulation, because since my discrete field is going to be discontinuous, I can basically write the two models and then add the suitable interface, a term in such a way that the coupling is handled in a pretty natural and weak way. Okay, these are the bilinear forms, and these are not very, I mean, they are ugly and full of formulas. It works from, at least from the verification viewpoint. And let me just show an example. Here we are. So this is an example of the pressure in, well, these try to mimic the physiological conditions. And the next step is, so the example I showed before is about only multiple network poroelasticity, and then we have carried out the simulation for the ventricle as well, and then we can merge the results. And this simulation has been done with Phoenix. So we have not yet moved to the full polyhedral grids, but this is on its way. Now, let me skip epileptic seizure because I don't have time, and I've been asked to address the most difficult questions. What's next? That's tough. So I'll share, well, my 5 cents. I don't want to be, I mean, this is like in any exercise of, this is not forecasting. This is where are we going? So let's start from the trends, or at least from what I perceive as trends. There are a number of them. I think this is a very important time for scientific computing. So first, the access to the exascale computing is now more pervasive, especially with the European initiatives. And that's one of the trends. There is a very urgent request of trying to design reliable digital twins for complex systems, complex and complex, so even more complex. There is the integration with computational learning techniques, so scientific computing, high-performance computing, and artificial intelligence. There is a trend for some extent automated science, so auto-simulations. And there's the quantum computing potential. So this, I thought a little bit, which are the trends of evolution, so trajectories, which we can see from now, but they are not fully realized. Some of them more, some of them less, but that's how I see the trends. And what I see as the role of scientific computing, or possibilities and challenges, of course. So on the one hand, there is always a very strong need of a physics-based modeling. I mean, the equations are there. It's reality, right? It's the word. First principles, they have an inherited predictive power, and they are inherently generalizable. On the other hand, we have a lot of data. That can be a source of information. For example, to tune the models, to inform. So any numerical method has parameter. So at a certain point, you can use the richness in the data to enhance the predictive power of computational methods and scientific computing. So I see that, well, at least from my perspective, the synergy between fully physics-based and the power of data can be a promising avenue. So where you use the power of data to enhance standard numerical methods, you use the richness of data to improve data simulation techniques to forecast uncertainty quantification. So to go from a deterministic setting into a setting where you have a variability. And you can, take the best of the two worlds. And this can contribute somehow to, enhancing what we know, which is the physics, with what we observe, which is the data, what we can measure, to improve current way of modeling and to model and solving numerically these models. But of course, there's no free lunch. So I foresee, well, at least a number that's a very incomplete list. It was the one that fit in the slides. There's the need of integrating domain knowledge. And that is particularly true whenever, for the applications, I'm interested, but this applies to any other kind of application. Problems are becoming so complex that you really need to grab knowledge from different fields. There's the issue of explainability and robustness. Then there's the issue that large-scale simulations cost a lot in terms of energy and infrastructures. So the next generation numerical algorithms has to be thought from the very beginning to be able to adapt to the future architectures and to be optimized in such a way that energy consumption is kept to a minimum, and then reproducibility. Otherwise, it's, I mean, one of the main pillars, luck. And then there's the quality of data and how data are produced and used, and how especially data which are sensitive are used whenever the application at hand is in domains where privacy and ethics is of paramount importance. And that's my last comment. So all these considerations cannot be, separated from the social implications and the ethical considerations. So scientific computing and their new avenue for scientific computing, like all technologies, there is a social and ethical implication. So I really think that bridging diverse expertise in terms of culture and background and attitude can really make the difference. There is a problem of making sure that scientific computing algorithms are fair compared to bias. And that's so there is the ethical question. So I choose the word responsible scientific computing. And that's it. So let me thank you for your attention. So I've been on time. And so let me thank you. Thanks for the funding. And the last thing I want to share, so all our codes are free, open source. It's a general library for the moment. It's just for students and, researchers. It's in 2D. The 3D is going to be available very soon. It's different models that you can patch together. So if you want to try, it's open for everybody. So thank you for your attention.
Great, thank you, Paola, for a very inspiring talk, both from the research you've done and for what your perspectives are for the future. I think Marie is in charge of the chat and the questions.
Yes, and I have a list of questions here. But let me thank you again, Paola, for a very nice talk, and also for addressing the challenge of looking into the crystal ball of the future. I think that's we very much appreciate it. Okay, so I thought I could start with some of the high-level questions that have appeared here. So working at the intersection between mathematics and the life sciences reveals a lot of potential and a sense of duality. On the one hand, there's the potential of mathematics and modeling in the application domain. But on the other hand, the new applications give new problems for mathematics. Would you agree? And do you have any thoughts on what are you most excited about in this?
Well, I fully agree. And I would say, well, that's a very personal viewpoint, but I would say that at least to me, the more interesting mathematical questions came discussing with colleagues from other disciplines. So with the medical doctors, with engineers, even with designers. Well, so we have a project with the designers, which is somehow perceived as a very far from mathematicians. And I think that this is really a characteristics that only mathematics and so applied mathematics share. So the ability to learn new languages, understand what are, the main important ingredients given the question. And the question, of course, come many different times from different field, and being able to abstract them and to categorize them and then use to solve them. And of course, most of the time, a method that works in a setting doesn't work in another setting. I mean, it's very hard to think that the same method will work for all possible regimes, all possible applications. But the idea is that you can then extend or improve or redefine in order to meet or try to answer to the application, to the questions that come from applications.
Thank you. I'll move on to another one here. So last week, Enrique Zuruzua talked about control and machine learning in this series, in particular control of dynamical systems and deep neural networks. Do you see any use of such techniques in your research?
Yes, I didn't mention, I think I've been so too quick. What are we doing right now? So many things, but let me mention this because it fits. I think it fits with Enrique's talk. So in the context of neurodegeneration, at least for the applications we are interested in, there is an incredible source of data that comes from cognitive tests. So in the clinical practice, patients given a certain scheduling, this is typically identified by the physicians according to how fast or how slow the pathology is evolving. Patient undergoes a panel of cognitive tests. This is a lot of information, which at least in our viewpoint, it's very difficult to be incorporated into a fully physics-based model. And then there's also what is called our cognitive reserve. So everybody of us has its own ability to put in place some mechanism to somehow slow down the pathology. So these are compensation mechanism. This is very personal. Doctors know, for example, that patients that have many years of study are slightly more prone to put in place such a compensation mechanism. Whereas, or for example, people that had a very intensive working life with a lot of cognitive responsibilities are slightly better in compensating. So we were finding a way to incorporating all these features into a model. So what we are doing right now is to use neural networks, so neural ODEs, to try to improve the evolution. So to use this huge set of data that comes from clinical tests, biomarkers. It seems that the blood biomarker, at least in the Italian national system, are going to be approved very soon, and not only for research, but also for clinical practice. So to use machine learning and neural ODE to learn from this very wide and broad set of data, which are broad in the nature, so cognitive tests, biomarkers, blood, and imaging, and so on, and very discontinuous temporally, because typically, for example, cerebrospinal fluid, you have only at the beginning, whereas cognitive tests, they are temporary scheduled to infer the evolution for a single patient. And this can serve as a complement, well, at least in our viewpoint, to a fully physics-based model. And ideally, then you would like to join them.
This sounds very fascinating. So, do I understand you then correctly in that you can also imagine controlling the evolution of the disease, maybe in the
That's
I guess that's
that's
yeah. It's a big question, but
that's a big question.
Maybe I should dare asking it.
Yeah, that's a bigger question. So there are many studies worldwide on new substances, on new therapies. Most of them fails on a say on a daily basis. So that's that's a tough.
Yes,
And
maybe we can
facing. I mean, the point is that I think that the World Health Organization it's estimating that by 2050, the number of people that will live with some form of dementia will triple. So, which means that's part of the aging. So we are going to, so the average age is increasing. And these kind of pathologies are very much age correlated for the reason I tried to explain at the beginning. And that's a social project of immense dimension. And most of the cost in terms of market, it's not for clinical practice, it's social cost, caregiving, so the impact on society. So I think this is going to be a very hard challenge in the next 20 years. But the research from the clinical practice, I mean, there are some progresses, a lot of things that are not yet fully understood on how our brain functions. So when we discuss with neurologists, so we ask questions, right, to better understand. We are not physicians, so we had to learn. And I was impressed by the number of times where they answer, well, on these things, there's not general consensus. But even on questions that I thought were really, low level, like, can you tell me exactly where the cerebrospinal fluid is produced? And the answer is, well, there's no general consensus. So there's a really, we lack, we as a scientific, worldwide scientific community, there are still a lot of things that are not fully understood from the biophysical and biological viewpoint. So.
And it sounds a very familiar culture shock coming from mathematics to the amount of things that there's not general consensus on in the neurology.
Very little can be measured. That's the point.
So so you answered much of the follow-up questions here, I think. So one aspect is this, that you can see the interplay between machine learning and scientific computing in two ways. Either you can think of it mainly as a way of augmenting the modeling, so hybrid models, or you can think of it as a way of devising new simulation strategies, right? And you mentioned one example here where you're using graph neural networks for agglomeration, for instance. So, and in your response, I'm very excited what you're doing now with the clinical data. There may be one of the ideas more on the hybrid modeling side.
So I think that really the best is to use them in a synergetic way. So physics is there. I mean, Newton's law is there. Is exactly our word, right? This is an invariant. So I think that surrogating the physics, it's not the best thing we can do. I mean, I think we can grab the best from the two approaches, which from the point of view as applied mathematicians and people from scientific computing community, there's a lot of possibilities and challenges and things to do. So I think that taking the best of the two approaches can really improve our modeling capabilities.
Thank you. Thank you so very much. We're running out of time. So
okay, yes.
Thank you so very much for the discussion. I'll give the word back to you, Thomas, to wrap it up here.
Yes, well, I'd just like to thank you once again, Paola, and also thank you for the discussion at the end. I think if you don't mind, we will also include that in the recording. I think it's just as valuable to people.
Yeah, sure.
Just a reminder, so there are a number of talks coming up in a couple of weeks. We'll have an Easter break next week, I believe, and then we'll be back in a few weeks. So please check the website for any updates. And yeah, thank you again for coming, and hope to see you soon. Bye-bye.
Thank you again for the invitation. I was really